And let's make sure that transcription is running. Let's check to see if transcription is running. Is it transcribing? Yes, good. All right, let me go ahead then and start Jupyter. So I'm just in a notebook in a terminal, and I'm going to open Jupyter Notebook, and we'll go to lecture 12. And for the past 11 lectures, well, for the first 5 lectures, we learned Python. For the next 2 or 3 lectures, for the next 3 lectures, we learned how audio works. And for the next 3 lectures after that, we learned how automatic speech recognition works. And then for the final 3 lectures of this course, we're going to be studying speech synthesis. We're going to learn how the speech signal is created in the human throat and how a computer can simulate the human speech signal. And then in the last lecture, you'll learn the application programmer interface that allows you to use the Google Speech synthesizer in Python. So first of all, today I just want to talk about how speech is produced. When we produce speech, your vocal folds vibrate. Your vocal folds are this pair of cartilages, actually a pair of tissues that string between the arytenoid cartilage in the back and the cricoid cartilage in the front. And these are a pair um, of tissue-covered muscles. So these are the vocalis muscles, and then over the top of the vocalis muscle, there's this kind of skin-like. Actually, it's called a mucosa. It's softer than skin, a soft sort of membrane over the top that flaps when air blows past it. And what happens is that when the vocal folds close, when air blows through them, they flap open and closed like a flag in the wind. Um, we can see this happening by putting a mirror into the back of your throat and by shining a bright light onto the mirror, and the bright light is reflected down to the vocal folds and then reflected back, and the doctor can see this happening. This can also be done using a fiberscope, and I want to show you a video taken using a fiberscope.
Here is a look at some normal young female vocal cords during a stroboscopic exam.
So this is a video taken from a fiber optic from a fiber that's strung through her nose so that it's pointing down into her throat. And you can see that here are the vocal folds. These are the folds that separate your lungs from your mouth. So below this is the trachea and then the mouth. The vocal folds here act to keep food from entering your lungs. So the vocal folds are brought together, and then as the air blows through the vocal folds, when you force air out of your lungs, it causes the vocal folds to vibrate back and forth 100 or 200 times per second. When it slows down like this, that's actually a strobe light. It's the same kind of strobe light that you would see in a disco. That strobe light is locked on to the speed of her vocal fold vibration, and so it flashes once every time the vocal folds vibrate, and in that way we can see it as if it was moving in slow motion. You can see it moving as if it was moving in slow motion. Now it's in slow motion. And so you saw it started out fast and then it locked in, and now it's showing it in slow motion. So we can see in slow motion how the vocal folds vibrate back and forth while the how the vocal folds vibrate back and forth because air is just blowing past them, and as the air blows past them, they vibrate back and forth like a flag flapping in the wind. And the air blowing through them looks something like this. The air increases as the vocal folds open, and then it decreases when the vocal folds close again. And then when the vocal folds are completely closed, the air cuts off. And so there's this sort of asymmetry where it starts out slowly and then ends abruptly. And that abrupt ending actually is where most of the sound occurs. So here's the air flow coming through the vocal folds. Here's the air pressure just above the vocal folds. When there's a lot of air coming up through the pipe, that increase in air causes a rise in air pressure relative to atmospheric pressure. When the air is suddenly cutting off, that cutting off of air causes a decrease in pressure relative to atmospheric pressure. And then when the air stops flowing entirely, that causes the pressure to suddenly return to baseline, back to atmospheric pressure. So we have this gradual increase in pressure and then a decrease in pressure and then a sudden cessation of all pressure. It suddenly stops entirely. And that sudden stop entirely happens 100 or 200 times per second. The spacing between this peak and this peak is 5 to 10 milliseconds. And that spacing turns out to be the most important feature. The tone that you hear, the ah, that tone is the tone of the period between these two peaks. One of these peaks happens 5 to 10 milliseconds before the other one. If it's 5 milliseconds earlier, then 1 over 5 is 200 hertz. If it's 10 milliseconds earlier, 1 over 10 is 100 hertz. So the spacing between these determines the pitch frequency. And so we can look at the most important feature of this is actually not this curved part. The most important feature is just this spike. Once every 5 or 10 milliseconds, there's this negative air pressure spike that then returns back to zero. And that spike happens T sub zero samples per pitch period. So the time from here to here is called T sub zero or T naught. That's the number of samples per pitch period. And that's equal to the pitch frequency. So if I sing a middle C, a middle A on a piano, that would be 440. I can't sing that high, but my voice is at around 110, which is at an A note 2 octaves below on the piano. We start out at middle A and then we go down 2 octaves and we get my normal speaking voice, which is 110 hertz, F0. If we divide Fs over F0, if Fs is 8,000 samples per second, divided by my pitch frequency of about 110 hertz, we get that my voice is occurring with about 73 samples per pitch period. From here to here is roughly 73 samples. And we can model this signal, this air pressure signal. We can model that air pressure signal very simply using a function E of n, which is a 0 most of the time, and it's only a 1 if n is an integer multiple of 73. So here it's a -1, here it's a -1. In between, we'll just set it to be 0 all the time. So let me say that 8,000 is the sampling frequency, 110 is my pitch, and T naught, the pitch in samples, is 8,000 over 110, which will be about 73. Then let me create an excitation signal, which is just a 1 second worth of zeros. And once every 73 samples, I'll create a -1. And then if I plot that, it looks something like the image that I had shown before. All right, Matplotlib is building the font cache. There we go. So it looks something like this. It's mostly zeros, but once every 73 samples, here's 73 and then 146. Once every 73 samples, it's a -1. And what that will sound like is a pitch at 110 hertz. That's the A note, 2 octaves below middle C on the piano, right? But that A note will be buzzy because it's not just a sine wave. In addition to the sine wave, we have all of the harmonics of that sine wave, all of the higher order harmonics. And so it will sound something like this. So you can hear that it is an A note, but that A note is buzzy, right? That it's buzzy because it has this sharp discontinuity. So we have that sharp buzzy sound because we have that discontinuity, the -1 and then all zeros, -1 and then all zeros, -1 and then all zeros. So now we've got speech, kind of. Now we've got speech up to the end of the neck, right? So if we look at a cross section of your head, now we've taken care of the pink part. And now we need to get the rest of the speech. Now we need to model the oral cavity and the nasal cavity. And what happens is that buzzing that's produced at your vocal folds, they're producing this sound that sounds like just a buzz. And that buzzing is being modified by the resonant frequencies of your oral cavity. Just like if you go in and take a shower, if you sing in the shower, you get these resonances, which are the echoes echoing back and forth inside the shower. In the same way, inside your mouth, this buzzing at your glottis is causing echoes that echo back and forth between your glottis and your lips. They look something like this. We have high pressure at the glottis and very low volume velocity, very low flow. In the middle of the vocal tract, we have lots of flow, but very little pressure. And here at your lips, if your lips are nearly closed, then you have very high pressure, but very low flow. And so the atoms of the air kind of bounce back and forth inside your vocal tract. And they bounce back and forth at whatever is the natural frequency of this length. In fact, this natural frequency will be such that this length from your vocal folds to your lips is 1/2 of a wavelength. So we can go in and calculate, okay, if what is the frequency at which this resonance happens exactly at the right frequency? That frequency is that frequency turns out to be around 500 hertz. All right, so we want to model this echoing back and forth, this echoing back and forth inside the vocal tract. We model it with a resonant filter that takes in E of n and generates a signal S of n. The sound that comes out of your lips is the buzzing from your vocal folds, modified by the resonances of the oral cavity. And those resonances can be modeled. This is basically we have force and velocity and position. So it's like a spring mass system in physics. And just like a spring mass system, we only need to model two variables. And it turns out that in digital signal processing, we only need to delay the signal once and then delay it again. If capital T is the sample time, then we have y of n minus 1 and y of n minus 2. So we create the speech signal and then we echo it back with one sample delay, and we echo it back again with a two sample delay. And if we scale those echoes just right, if the amplitude of those echoes is just the right amplitude and we add them together, then what we get at the output is a resonance at a particular frequency. And what are those scalings? What is B and what is C? Well, those have been calculated for us, and let's just take the formulas out of this article. This article is from 1979, I think. 1970. Let's look it up. This article is from 1980. Okay. So we'll take this article from 1980, and this article gives us exactly what the formulas are for those feedback coefficients. The feedback coefficient C that multiplies y of n minus 2, that feedback coefficient is negative e to the minus 2 pi times the bandwidth times the sample time. Capital T is the sample time, it's 1 over fs. The feedback coefficient B is 2 times e to the minus pi bandwidth times sample time times cosine of 2 pi times the formant frequency f times the sample time t. Writing those in terms of Python, we have that C is equal to negative e to the minus 2 pi bandwidth over fs, and B is 2 times e to the minus pi bandwidth over fs times the cosine of 2 pi times the formant frequency over fs. And so if we scale by just exactly these coefficients and feed them back and add them together, take the input and add it to these two feedback terms, then we can simulate this kind of resonant behavior where we get a resonant echo inside a small chamber. In this case, the small chamber is your mouth. So we'll just create y of n is equal to a times x of n plus b times y of n minus 1 plus c times y of n minus 2. Let me write the code. I'll define a function called resonator that will take the bandwidth of that resonance, the frequency of that resonance, and the sampling frequency. And it'll calculate the coefficient c and the coefficient b, and the coefficient a is 1 minus b minus c. Then it'll create a series of zeros, and the first output sample will just be a times the input. The second output sample is a times the input plus b times y of 0. And every sample after that is just a times x of n plus b times y of n minus 1 plus c times y of n minus 2. Let me define that function, and then let me create a resonance at 500 hertz with a 100 hertz bandwidth. And that looks something like this. And now you can see that I've taken the input excitation. Remember, the excitation is just this buzz, a negative pulse, negative pulse, negative pulse. That negative pulse now excites something that looks like a decaying sine wave, right? We get this big pulse at the beginning where the vocal folds slam shut, and we get this negative pressure spike. Negative pressure then bounces back and forth inside the vocal tract. This is that bouncing back and forth of that negative pressure spike inside the vocal tract. And if we listen to it, it sounds like. Let me play you both of those. Here's the original here's the original vocal folds excitation, the excitation caused by the closing of your vocal folds. That's just a buzz, right? But now that I've filtered it through this resonance, it sounds like kind of like when you blow on a bottle or you sing in the shower. It sounds resonant. Oh, right? So we have this echoing resonance, and you can see it in the waveform. You can see that echoing back and forth of that resonance in the waveform, and you can hear it kind of as a tone. There's the tone at which is being excited, 110 hertz. But above that, there's this frequency. This frequency is called F1. So this spacing is called F0. This bouncing back and forth is called F1. It doesn't sound like speech yet because speech has more than one resonance. This is F0 being played through an F1 resonator, but speech has at least four resonances. Speech has an infinite number of resonances. The first two determine what kind of vowel it is. The first four determine the way that the person sounds. So different people will have slightly different frequencies for F3 and F4, slightly different bandwidths. And those resonances look something like this. The atoms at the lowest frequency, the atoms are bouncing back and forth inside your whole mouth, from your glottis to your lips, from your throat. Here's your throat, here's your lips, and the atoms are bouncing back and forth. At the next higher frequency, the atoms are bouncing back and forth separately in the back half and the front half of the vocal tract. As they bounce forward in the back half, at the same time, they're bouncing backward in the front half, and air pressure builds up in the middle. And that buildup of air pressure in the middle then drives them away, drives them backwards. And so we get this bouncing back and forth over half of the length of the vocal tract. In the third resonance, they're bouncing back and forth over 1/3 of the length. In the fourth resonance, they're bouncing back and forth over 1/4 of the length of the vocal tract. Each of these is just a spring mass system. And so for each of these, we can model it using a second order resonator. The first resonator will be F1, the second resonator will be F2, the third will be F3, and the fourth will be F4. For the vowel ah, for a male speaker, those formants and bandwidths are something like 700, 1200, 2500, and 3500 hertz, and the bandwidths are something like 100, 200, 300, and 400. The bandwidths don't have to be exactly right. They can be, off by plus or minus 20 hertz. It doesn't really matter that much. So we'll just make them multiples of 100. And so what I'll do is I'll take the excitation and pass it through a resonator with a frequency of 700 and a bandwidth of 100. And here's the output, Y1. This is this arrow in this chart. The output from the first resonator to the second resonator goes through this arrow, this wire. And here it is, that Y1 is now the input to the second resonator, right? Y1 is the output of the first resonator. It's the input to the second resonator. The second resonator has a frequency of 1200, the third resonator at 2500, the fourth resonator at 3500. And then finally, the output of the fourth resonator over here is the speech signal. So we get the speech signal finally as the output. And if we listen to that, now it will sound artificial. Now we can look at it. We can see here, you can see the air bouncing back and forth at the first frequency. But you can also see that it's being modified by some higher frequency information. Those higher frequencies are 1200, 2500, and 3500. So up here we had this kind of very mellow bouncing back and forth at F1, and it sounded like this. Down here we have this much more jagged bouncing back and forth where we're adding together all of those resonants, all of those formants. And if we play it, it sounds like this. And now we have something that sounds robotic, but it sounds clearly like an ah vowel. Now we've created speech. That's all it takes to create speech. We have a resonator with the first formant, the second formant, the third formant, and the fourth formant. And after we add together all of those formants, we get something that sounds like a vowel. All right. So now we have everything we need to create speech, and now we just need to modify those frequencies. I told you these are the frequencies for ah. If you want some other vowel, you just need to change those frequencies. And so let's look at that. The voice source just sets the pitch of your speech. So F0 is how often do your vocal folds close. The vocal tract is the air passage between your glottis and the lips, and that determines the sounds of this which vowel is being produced. And we can look at a real-time MRI. Let's watch a real-time MRI to see how your tongue moves up and down inside your vocal tract.
Welcome to the Science Gallery of the Max Planck Society.
Okay, so notice as he says welcome, as he says the in welcome, his tongue will move up because the sound has your tongue moved up. And then as he says come, his tongue will move down into the sound. Um, welcome, right? So you saw he said welcome. When he said well, his tongue went up. When he said come, his tongue moved down. That movement of the tongue back and forth creates the different resonant frequencies that characterize the different vowels of speech. Here are the vowels of Swedish. I couldn't find a good example showing the vowels of English, but they're kind of here. Here's E, A, O, U, the vowels of Japanese and Spanish. So you can see that, let's see, what are these? This is F1. This is the first formant, and it's kind of scaled going down from 200 down to 900. So E, A, the first formant goes from about 300 to 450 to about 700 hertz. And then when we go to O, we're back to 450. O and A have almost the same F1. E and U have almost the same F1. It's at around 300 hertz. So E, A, O, U. What happens in between is that the tongue moves down and then the tongue moves back and up. When we go to O and U, the tongue moves back into your mouth and up. And so that front to back movement from E to U changes F2. The second formant frequency is at around 800 hertz for U, around 1000 hertz for O. For A, it's at around 1200 hertz. For A, it's at around 1900 hertz. And for E, it's way up there at around 2100 hertz. And so we find that, notice that this is just F1 and F2. All of the others, F3, F4, and all the bandwidths can be just fixed. Those F3, F4, and all of the bandwidths determine which speaker is talking. As you change these, they change sort of your percept of the speaker, but they don't really change the vowel. F3 can be used to make some distinctive vowels in Chinese or in Swedish, but in English or in Japanese, F3 is not really used to distinguish vowels. It is used to distinguish some of the consonants in both English and Japanese. So we can create the five vowels of Japanese by creating an F1 dictionary. Ah has an F1 of about 700. Well, yeah, there it is, 700. E has an F1 of about 350. U is also 350. A has an F1 of about 450, and O is also about 450 or 500. A and O are almost the same. For F2, A is at around 1200 hertz, and then E is at 2100, and U is really low at 850. A is really high at 1900 and O is really low at 950. So we can take this dictionary mapping from the vowel a, e, u, a, o to the frequencies F1 and F2, and then let's just use the resonator to make them. We'll take 5 different phonemes, a, e, u, a, o. For each of those phonemes, I'll get a plot number. The plot number will be 0, 1, 2, 3, 4, right? So for each of them, I'll take the same excitation signal and I'll pass it through a resonator at F1, then take the output of that, Y1, and pass it through a resonator at F2, and then take the output of that and pass it through a resonator at 2500, take the output of that and pass it through a resonator at 3500. So we get A, E, U, A, O with these 4 resonant frequencies. And if we plot all of those vowels, we get here's what the waveform for A looks like. Here's the waveform for E. Here's the waveform for U, A, and O. Let's listen to them. The way that I've done to listen to them is to concatenate the speech followed by 1 second of zeros. Right, so I have the speech each time with Y4, the output of the last resonator, concatenated with zeros. So we'll have A, E, U, A, O, each one of them separated by a silence. Right, so I think you can hear it's very robotic, but it's starting to be intelligible. You can hear the vowels A, E, U, A, O. All right, let's try to do this week's homework. We have 3 functions that we want to write. One is voiced excitation. So let's look at the docstring for that. We want to take as input the duration of the waveform, the pitch frequency, and the sampling frequency, and return a NumPy array such that that excitation is 0 most of the time and only -1 if n is an integer multiple of t naught. So let's create that function. We'll get rid of the runtime error. And we want to create, let's say T naught is equal to the integer of Fs over F naught. That's the pitch period in samples. We want to create an excitation signal, which will be zeros of a length of duration. And then we want to create -1 once every T naught samples. And I think that's all. Let's return that excitation and see if that solves the problem. Let me save that Python file. And then let's run that and see if we get the waveform that looks right. There we go. It looks like the first 300 samples of a simple speech excitation signal. Let me add something here to IPython display excitation. Oh, it's IPython display audio data equals excitation. And how do I specify the rate? Rate equals. All right, good. That's the buzz that we were looking for. So we've created this buzz. All right, the second problem will be to recreate that resonator. We want to take in the formant frequency, the bandwidth, and the sampling rate, and we want to return, we've got an X, which is the excitation, and from that excitation, we want to create that resonant output. So let's go ahead and see if we can create that. Let's see if I can remember these coefficients without having to look them up. I think C is negative exponent of pi times the bandwidth over Fs. And I think that B is equal to 2 times e to the pi times bandwidth over Fs times the cosine of 2 pi times the formant frequency over Fs. If I get those wrong, then I'll go back and fix them. We'll be able to tell because if I get them wrong, then it will sound like nothing. But let's try it and just see if it works. So we'll create an output signal y, which should be exactly as long as the input signal x. And then y of 0 is just a times x of 0. And y of 1 is a times x of 1 plus b times y of 0. And then for n in the range from 2 to the length of x, I want to say that y of n is equal to a times x of n plus b times y of n minus 1 plus c times y of n minus 2. And then we return y. All right, I think I've just recreated exactly the same thing that was in the resonator function in the notebook. Let's see if that worked. Oh, I need to specify that this is either NumPy cosine or math cosine. Let's try that again. Nope, that doesn't look correct. All right, well then I must have got the coefficients wrong. Let's go back and look and see how I misread the coefficients. C should be negative e to the 2 pi bandwidth over fs. Ah, that's the reason. Negative e to the 2 pi bandwidth over fs. And b should be 2 times e to the negative pi bandwidth over fs times the cosine of 2 pi f over fs. Okay, I think that's now correct. Let's test it and find out. Negative e to the 2 pi bandwidth over fs. I'm reloading it and it doesn't look right. Well, let me copy from the notebook here and see if that changes it. C is negative e to the negative 2 pi. There we go. Bandwidth over fs. B is 2 times e to the negative pi bandwidth over fs times the cosine of 2 pi f over fs is 1 minus b minus c. All right. The rest of it looks correct. Let's try that again and see if it works now. Ah, there we go. That looks right. Let me go ahead and add an extra window here and try IPython display audio. Data equals resonance, rate equals fs. All right, that sounds like the resonant buzz that we were expecting. And now finally, we want to synthesize a vowel. If we print out the doc string, we see that we have a duration, which is the duration in samples. And then we have F0, F1, F2, F3, F4, bandwidth 1, 2, 3, 4, and Fs. And we'll put that together by actually taking the voiced excitation as our first function. Let's copy down here. We want get rid of the runtime error. We want to say that the excitation, we'll get that by passing into the voiced excitation the duration, F0 and Fs. And then we want to pass that excitation through the resonator 4 times in a row. And then we just return that. Y4 is the output of the final resonator, so Y4 should have the Y4 should have the speech in it. We've passed the excitation in and got Y1, passed Y1 in and got Y2, passed Y2 in and got Y3, passed Y3 in and got Y4. So let's try that and see if that works. We missed FS as a, let's see, the resonator needs FS as an argument. So let me add FS to each of these. Oh, I forgot to put FS in the very first resonator. There we go. The resonator needs to know what the sampling frequency is. There we go. There's A, E, U, A, O. Let's just play it to make sure that it sounds right. Let's see. We have speech is being created. Oh, we've created A, E, U, A, O. So the very last one should be the um, very last one should be just the O. Let me actually create speech as a dictionary here so I can play all of them. Let's say that speech of phoneme is equal to synthesized vowel, and this will be speech of phoneme colon to 300. Let's see, there we go. Now we've got A, E, U, A, O, and now I should be able to play data is speech of each vowel separately and see what they sound like. So if I play the A first, and now I'll play the E, and now the U, and now the A, and now the O. All right, so we've managed to synthesize all 5 vowels. Let's just check to make sure that the grading code agrees that we've done those correctly, and it does. It says score 100%. All right, very good. Well then, let me go ahead and check it into GitHub. All right, homework 12. Let's push it to the origin. All right, and let me go to GitHub to make sure that that worked. All right, good. There's all the computations. There's all the code. So we can then just copy this and go to the oh, we don't have the original intro speech understanding here. So let's find the let me log into KCG so we can find the homework. There you go. And then just copy your URL into homework12.py and once those are there, I will grade those. That's all for today. So let me stop the recording.